All right, so first of all, we talk about the stoichiometry. Stoichiometry, the backbone of the stoichiometry is mole to mole ratio stoichiometry. So usually when people talk about stoichiometry, that is the stoichiometry from mole of something based on the coefficient on the chemical equation and find the moles of others. So that is called the stoichiometry. Okay, and there's some of the variation for the stoichiometry. One of the variation is I giving you the mass of certain chemicals, and then I'm asking for how many mass of the other chemicals will be generated or consumed based on the chemical reactions, right? But this is still stoichiometry. It's just a mass to mole and mole to moles and mole to mass stoichiometry. The only difference is you need to convert the mass to the mole first, which is we need to know how many molecules that are in there so we can using the coefficient to make the proportional to calculate what is the next the product or the reactant. Okay, so that's a mass to mole. You convert that to mole, and then in the end, once you figure out the moles of the chemicals, then you're going to convert to the mass, which is using the molar mass again. Right, the conversion over here is the molar mass. We're using molar mass to convert between mass to mole, and we using mole still using molar mass to convert from mole to mass, right? Because we know mole is equal to mass over the molar mass of that chemicals, and the mass should be equal to mole multiply the molar mass of that chemicals, right? So this is one of the way for the stoichiometry. Well, obviously there's another stoichiometry way. Okay, we haven't talked about it. There's a way, because you remember, as long as we can figure out mole, and then we can solve the stoichiometry. We talked about before. Did you still remember what things can also convert to mole? We know mass can convert to mole. And we also talk about there's one more concept, one more thing that can also convert to mole. Still remember? Molecule numbers, right? Yeah, or atom numbers, right? We talk about the molecule numbers can also convert to mole, because no, in this case, we're just using Avogadro's number to convert between, right? Because 1 mole of the substance has 6.02 times 10 to the 23rd of that numbers. That makes sense, right? So if you know the molecule numbers, you can also figure out the mole. So that's why there's another variation, which is I telling you what is the molecules number for these reactions, and then you try to figure out how many moles, how many molecule numbers can figure out based on others. For example, I have hydrogen gases react with oxygen gases. Then after the lightning ignition, we're going to generate the water vapor. So in this case, let's say it's balanced in this way. So now 2 moles of hydrogen will generate 2 moles of water. 1 mole of oxygen generate 2 moles of water. So now I'm saying I have 4.5 times 10 to the 22 the atoms of the oxygen. Then how many atoms, how many molecules, not the atoms, how many molecules of water will be generated. Okay, this question is not shown in the study guide, but it's similar. So now you see what we have is the atoms of the oxygen. So we know the atoms of the oxygen over here. And then we try to ask, okay, how many molecules of the water can generate it? Then that's going to be the same thing, right? We're basing the stoichiometry, the moles of the molecule numbers, and you figure out how many moles of there, and using how many moles of numbers to convert moles of the water molecules, and then figure out how many numbers of that. That's also thing. Also fine. So this is molecules. Okay, yeah. So now you can do the three steps. The first step, you convert. First step is just using the atoms of oxygen. You convert that to the mole of oxygens. This is the first step. Second step, you're figure out based on the stoichiometry. That step is stoichiometry, using moles of oxygen to figure out moles of the water. Right? Yeah. And then the last step is using mole of the water and to find molecules of water. Okay, yeah. So still the three steps, just like what we do for the grams, is almost similar. The number two is the stoichiometry. The other two, number one and number three steps is just conversion between molecule numbers and mole. That's it. Does it make sense, right? Yeah. So you see, stoichiometry is just the backbone of this. The other steps is just try to help you to convert that to the moles. Okay, yeah, so we can still doing the same thing like this. Okay, so first of all, you're going to figure out the mole of oxygens. Then the moles of oxygen is just using the molecule number or atom numbers of the oxygen, 4.5 times 10 to the 22. This is atoms of the oxygen, and it divided by 1 mole of the oxygen should have 6.02 times 10 to the 23rd of the atoms of oxygen. Okay, then you will figure out how many moles of that. Okay, this is per mole. All right, so let's just figure out this. (4.5 times 10 to the 22nd) divided by parenthesis 6.02 times 10 to the 23rd. Then we got this 0.07475. And I recommend if you do the stoichiometry step by step, which is 3 steps, it's better not round this number too short. For example, in this case, please do not round like a 0.075. You're going to keep enough the digit. So in the final answer, you will make it more accurate. Okay. Yeah. So in this case, I prefer keep 4 decimals, 4 sig fig, 0.07475. And that is a mole. Okay. This is how you got the moles of oxygen. And then you based on the stoichiometry, you can figure out the moles of water by the moles of oxygen, right? The mole of the water, that should be equal to moles of oxygen, 0.07475 moles of oxygen. Then you cancel 1 mole of the oxygen can generate 2 moles of the water. right? So now you can base on this to figure out moles of water. 0.1495. And that's going to be the moles of the water that it can generate based on the moles of oxygen. And then you base on moles of water, based on moles of water, figure out how many molecules that it can have. So the molecules number of water is just equal to moles of water multiplied 6.02 times 10 to the 23rd. 0.1495 mole times 6.02 times 10 to the 23rd. And that's going to be a 8.9, well, 8.9999. 8.9999 times 10 to the 23rd. No, 22. Okay, times 10 to the 20th. So then if you're looking at the question gave you like a 2 sig fig. So answer will keep 2 sig fig. So answer will be 9.0 times 10 to the 20 seconds. And this is how many numbers of the water molecules. Okay, that makes sense, right? So stoichiometry, the backbone of the stoichiometry is just mole to mole ratio. Okay, it really doesn't matter how you figure out the moles. Okay, the backbone is a mole to mole ratio. As long as you know that part, and the other steps is just helping you to get the moles or to convert the mole to other stuff. Or even for this question, you even don't have to figure out the moles, right? The molecule numbers. You can figure out the grams of the waters, right? It's the same thing, right? It's just giving you the molecule numbers, convert to mole of water, and then if the question asking for how many grams of the waters, then you just convert the moles of water to the mass of the water. That's it, right? Yeah. So that is just the stoichiometry, and there's a lot of different variations. Because the reason they have the variation is because there's something that can convert that to mole, and the mole can also convert to something else. That makes sense, right? Okay, so this is again what we talk about here. And one thing I need to emphasize, okay, how do you, last time we talked about the limiting reagent, right? Limiting reagent is also talking about the stoichiometry. But I'm giving you this question. How can you tell this question is just a simple stoichiometry? And the other question could be the limiting reagent problem. How? Just telling you one of these trick things. So let's looking at one of the real limiting reagent question. Let's looking at the question number. First of all, I would like to check in your study guides. Do you have a page 24? Last page. If you don't have a page 24, raise your hand. I will give you the new one. Everyone has the page 24. Okay, and that's great. Okay, if you're looking at the question 10 in the page 24, then you will see, you see, they give you the chemical equations, conceptual question equation. Then they said the combination of a 2.00 moles of X with 2.00 moles of the Y produce 1.75 moles of Z. And then they are asking for the percent yield of the reactions. I will talk about what is the percent yield. But if you're looking at the first part of these questions, did you see what's the difference between the question I gave you over here? My question is here is that I have a 4.5 times 10 to the 20 seconds atoms of the oxygen. Then how many molecules of water will be generated? And then I'm talking about this is just a normal stoichiometry. But if you're looking at the limiting reagent, they said we have 2.0 moles of X and 2.0 moles of Y. Then they're asking for limiting reagent. Did you see the difference? I'm not talking about one is giving you the molecule numbers and the other one give your moles. But here you see in the normal stoichiometry, they only just telling you the number, one number. You see, you give your one number of certain something. So in these equations, I only tell you the numbers of the oxygen, which means I only talk about the oxygen. I didn't talk about hydrogen. I didn't give you the number of hydrogen over here. Right? So that means I assume the hydrogen is unlimited. Okay? But if you're looking at the limiting reagent question, what is that set? They talk about both the X and the Y. Right? They give you both the numbers for the both reactants. That is the difference. Okay, limiting reagents, they always telling you the both the numbers for both reactants. But for the stoichiometry, they only telling you one of them. Okay, yeah. So that is the major difference between limiting reagents and the normal stoichiometry question. Make sense? Okay, yeah. Okay, so let's just jump to the limiting reagent. Okay, I know we already talked about this, but it's been a way for the limiting reagent. Let's just remember ourselves. Let's recall what is a limiting reagent. Do you still remember the definition for the limiting reagent? Yes, Klein. First reacted, right? Is limiting reagent is the one that used up first. It doesn't mean they have a smallest amount, but they are going to use up first. Okay, so the limiting reagent is a completely used up. The excess one, doesn't matter how much the excess one has, they're still going to stop. The reaction will stop there. Okay, it's not going to have any more reactions. That's it. That's it. So that is the limiting reagent, right? Just like you're making hamburgers. If you're running out of the burger, doesn't matter how much meat you have, you're still not going to making a hamburger. You can make a meat, but you're not going to making a hamburger, right? So that is the limiting reagent. So that is why. Okay, so the first one running out. So let's looking at these questions. Okay, let's work on this, and then we will figure out the real questions. Okay, so this is the real questions. Let's just looking at this. We have a 2x plus 3y's, and then they're going to form 3 of the z's. They're going to form 3 of the z's. And then here, this question asking said, we have a 2.00 moles of x and also have a 2.00 moles of the y, and then we try to figure out what is the, so let's don't worry about what is the percent yield, talk about, let's first figure out, okay, what is the limiting reagent over there? So did you still recall how do we figure out the limiting reagent in the video? Let's just recall. Okay, so in the video, they talk about, okay, we need to do 2 assumptions. The first assumption is, if we use up all the 2 moles of x, which means if we use up all of the x, how much moles of y that we're going to generate, we're going to use up. And if we use up 2 moles of y, how many moles of the x that we are going to react with. So we're going to just using those, compare those 2 numbers and figure out what is the limiting reagent. Okay, so let's figure out. So if we want to using 2 moles of x, how many moles of y that we're going to use? That is a stoichiometry, right? We have 2 moles of the y's, now 2 moles of x. and we try to figure out how many moles of Y that are going to react, then just based on the coefficient. 2 moles of Y need to react with 3 moles of X. So 2 moles of X need to react with 3 moles of Y. So 3 moles of the Y. Moles of X, moles of cancels, then we got 3.00 moles of the Y. In another word, if we use up all the moles of the X, we should use up 3 moles of Y. And actually, just based on this, you will already figure out what is the limiting reagent. Because think about it, if I use 2 moles of X, I need to use 3 moles of Y. How many moles of Y do we have? We have 2 moles of Y. So that's impossible for this reaction to consume 3 moles of Y. That makes sense, right? Because we only have 2 moles of Y in this reaction. So 3 moles of Y is impossible to be consumed. So that is why Y will be the limiting reagent, because we're short of the Y. So we can only consume 2 moles of Y. When we consume 2 moles of Y, obviously, we're not going to completely consume the moles of X over here. That makes sense? Yeah, I know this part is confusing. Yes, yeah. So, all right. Then let's just looking at if we use up 2.0 moles of the Y, how many moles of X that we can consume? 3 moles of the Y will react with 2 moles of the X. So moles of Y canceled. Now you will got 4 divided by 3. 4 divided by 3, that's going to be 1.333 mole of the X. Okay, so in another word, if we want to consume all moles of the Y, which is 2.0 mole of the Y, I only just need to consume 1.33 moles of X. And do we have that enough of the X? Yes, we have 2 moles of the X. So it's more than enough than the 1.33 moles of the X, right? So that means if the reaction is a stop, we still have 2.00 moles of the X, subtract 1.333 moles of the X. We still have some of the excess, which is the leftover moles of X over there. Does that make sense? I know this part is confusing, okay? Yeah, so this is what the video shows. But usually I don't do this, okay? I have an easier way to demonstrate which one is the limiting reagent and which one is the product, okay? So let's looking at over here, okay? I'm going to talk about my way. It doesn't matter which one you think familiar, okay? Or you think is easier to be understood. So my way is not talking about, I'm not going to calculate, okay, if I consume all of the X, how many moles of Y we're going to use up? If we consume all of the Y, how many moles of X we're consume? And then we compare this to figure out the limiting reagent. My way is try to figure out the product, okay? So I consume, but we're still going to do the 2 assumptions, but this assumption is just talking about the same product. So my way is, if I consume all of the X, how many moles of Z that we're going to produce? And the other assumption is, if I'm using all of the Y, how many moles of the Z that we can produce? So now we're just we're using the same the reactant to figure out the product, which is the same product. Okay, so let's just looking that. So this is my way. Okay, so now if I using 2 moles of the X, now how many Z that we're going to produce? So 2 moles of the X will produce 3 moles of the Z. So moles of the X canceled. We're going to produce 3 moles of the Z. Okay, so this is the first assumption. If I using up all of the X, how many Z that produce? Second one is, if I use up all of the Y, how many moles of the Z that we can produce? 3 moles of the Y, that is going to produce 3 moles of the Z. Okay, so in this case, moles of Y canceled. Now we got 2.00 mole of the Z. Okay, so now once we figure out the 2 assumption of here, then what are we gonna do? We're just compare the moles of Z. Since we have 2 of the moles of Z here, we're just gonna compare the same moles of Z. Based on the Y, we produce 2 moles of Z. Based on the X, we produce 3 moles of Z. And then what are we gonna do? We're going to choose the one has the smallest number. Okay, so 2 moles of the Z will be what we call the theoretical yield. 2 moles of the Z will call the theoretical yield. The theoretical yield is the maximum production that can generate it based on the limiting reagent. Okay, the theoretical yield is the maximum product that can be generated from the limiting reagent. Okay, so theoretical yield is the maximum product that can be generated from the limiting reagent. Okay, so you see, you're compared the same thing, Z, but we're going to choose the smallest. The smallest one is called the theoretical yield. Okay, and then what makes this smallest? Y. Y is making that as the smallest. So Y is what we call the limiting reagent. Okay, now you see, just based on this equation, we can figure out both 2 things. First, we figure out which one is the theoretical yield, and then we figure out which one is a limiting reagent. Again, limiting reagent is the reactant, and the theoretical yield is the product. So this one is more straightforward than this one, right? I know this one is getting confusing because the first time when I learned this, I got totally lost. I have no idea how to compare those 2 to figure out which one is the limiting reagent. But if I do this, I just compare the number. I'm going to choose the smallest number, and then I know the smallest number is the theoretical yield, and which one makes the smallest number and is called the limiting reagent. That makes sense? Okay, yeah. So now, so this is the limiting reagent. In this case, we know 2.00 moles of Z will be theoretical yield, which means based on the limiting reagent Y, we can only produce the maximum number of the yield, the product of Z that we can generate is 2.00 mole. There's no way that we can generate 3.0 moles of the Z because Y is already completely consumed. Okay, so once the Y is consumed, no more Z can be generated. No more Z can be generated. Are you clear? Erica, do you have any question? I know this one need to be calculated, need to be practiced. All right, so the next part is, now let's start to talk about what is called theoretical yield and what is called experimental yield. And what is called yield percent or percent yield. Theoretical yield we already talked about, which means is the maximum amount of the product that can be generated based on the limiting reagent. So that is the maximum product that can generate it based on the limiting reagent. So that is called a theoretical yield. So what is the experimental yield? Experimental yield is experimentally, if you're doing the lab, okay, you're doing the same experiment, okay, and in the experiment, how much of the product you can gain from your experiment. That is called the experimental yield. Okay, just give you one example, right? I mean, every morning I like to eat 2 eggs and 2 breads, okay, with the peanut butter, okay. But sometimes, okay, when I wake up, I feel uncomfortable. I'm not going to eat eggs. I just eat the 1 bread of the 1 bread. Then you see, technically, theoretically, what I eat is 2 bread and 2 eggs. But experimentally, at that certain day, I can only just eat 1 bread. So you know the difference, right? Theoretical yield and experimental yield. And what is the percent yield? Percent yield is an equation just between experimental yield divided by the theoretical yield. And your time 100%. Okay, so that's it. In other words, but what is my percent yield for my breakfast? It's just 1 bread, 1 divided by 4, and time 100%. Okay, which is I got 25%. That is my percent yield. That makes sense, right? So that's its difference. All right, so now we already figured out the theoretical yield in this experiment is 2.00 moles of the Z. And if you're looking at carefully in the question already gave you the experimental yield. And just to let you know, if you're just looking at the questions, usually the question will telling you what is the percent yield. Okay, yeah. Sorry, what is the experimental yield? Because you don't have a chance to do the lab to gain the experimental yield. So the question should give you what is the experimental yield. So they said we have 2 moles of X with 2 moles of Y, then produce 1.75 moles of the Z. So the 1.75 moles of Z here, that's gonna be the experimental yield. So the experimental yield is 1.75 mole of the Z. Okay, so the percent yield over here, that's just experimental yield, 1.75 moles of the Z divided by 2.00 moles of the Z, and then your time 100%. Then the answer will be 0.85, which is 875, which is equal to 87.5%. Are you clear? I know this one is pretty confusing. Okay, yeah. I don't expect everyone will understand this at the first time. You definitely need to do the practice. Okay, you definitely need to do the practice. So let's looking at the first question, question number 7. Okay, so please go ahead to work on the question 7 and figure out what is the limiting reagent, and then to determine what is the amount of the excess reactant. Question number 7. So really doesn't matter which way you're using to figure out the limiting reagent, but first you need to find the limiting reagent.
But this is the aluminum, so it's not that ratio. So this aluminum over the result of the monoxide is back.
Oh, you're doing the, you're not just doing the calculation. Fine.
Yeah, so I will do this consistent with this. I can set it up as fractions.
Okay, yeah, that's fine. This is also, usually, another easy way, if you're familiar like this, there's another easy way if you want to figure out this case number, this is divided by. Yeah, so usually, if you have oxygen, it's not about the oxygen and combination, that's it. Yeah. So this is usually what happens. Because of 2 moles of oxygen will produce a 3 positions. So in the outside was 2, so that's be 2. Okay. Which one has more support? Based on the data model, why 6 is divided by 6, where the 6. Let's go 6 shows up here. No. Just the coefficient. So we just, because you talk about option, let's not talk about option. Okay? So coefficient, and also you try to cancel most of option, and you try to figure out the most of the element. You're using 6/6, where is the most of the element? You're using the ratio 3 and use the ratio 2. Yeah, because you try to cancel, you say most of oxygen first, so you cancel most of oxygen. Most of oxygen is first, so you first 3. Yes. Then you are looking for most of the aluminum oxide, so you put most of the aluminum oxide. In front of that is 2, so that's 2 and 3. Here doing the same thing. We're using 4.5 moles of aluminum. The ratio is 4:2. Try to cancel the aluminum. Try to extract the moles of the aluminum oxide. So that's why it's just the coefficient. Don't think too much. Okay, just the number on in front of this. That's it.
Thank you.
Okay. Axis is the product, right? So you based on this, you figure out which one is it. This aluminum, right? Which means oxygen will be the axis. Right? Oxygen is axis. Then the meaning of the axis is if you use up all the aluminum, the oxygen is not going to be used up. Oxygen still has some left over. I just try to figure out how many left over. And how to figure out the left over? You already have the oxygen most of oxygen, right? And then you know the limiting ratio is one, which means the oxygen should be used up. So if we then just set another stoichiometry, try to figure out that if we use up this only 5 moles of aluminum, how many moles of oxygen? And then in this case, you will know one aluminum is a gun with how many moles of oxygen. And the difference between this and most of oxygen here is going to be that, because we know aluminum is used up, I'm going to use some of the oxygen, but this oxygen still have left over. And the difference will be just enough. Okay.
All right, so let's review these questions. Yeah, I know that this is your first time to do the practice. It's getting confusing. That's normal. Okay, you just need to repeatedly to doing the similar practice and understand that. Okay, the more practice you do, the better understanding you will have. Okay, so now we have the 4 moles of aluminum react with the 3 moles of oxygen. then we produce 2 moles of the aluminum oxide. That's just a stoichiometry, right? Again, you need to set up 2 of the stoichiometry to figure out which one is the limiting reagent. I have a 4.5 moles of aluminum. I have a 3.5 moles of the oxygen. So first, the idea is if we use up all moles of the aluminum, how many moles of the aluminum oxide that we can produce? Well, that's just a 4:2 ratio. We have a 4 moles of aluminum, and then we're going to gain 2 moles of the aluminum oxide. Okay, so 4.5 times 2, which is 9, divided by 4. That's going to be 2.25. So based on moles of the aluminum, we can figure out, we can generate 2.25 moles of the aluminum oxide. And then if we use up all the oxygen, which is 3.5 moles of the oxygen, and then based on moles of oxygen, how many moles of the aluminum oxide that we can generate it? Moles of oxygen canceled, that's a 7 divided by 3. 2.333. 2.333 moles of the aluminum oxide. See, those 2 are all aluminum oxide. Those are all the product. And then we just need to compare those 2 numbers. And we talk about which one is the theoretical yield, or which one is the maximum amount that can be produced by the limiting reagent is the smaller one, right? So that means that this guy will be the theoretical yield. So later, if you want to figure out the percent yield, you're going to using this number, not using this number, okay? So where this come from is coming from the aluminum. In another word, aluminum will be the limiting reagent. Okay, aluminum will be the limiting reagent. All right, so now we figure out what is the limiting reagent, but then the question is asking for determining the amount of the excess reactant, which means they talk about excess. In other words, if the aluminum is the limiting reagent, that means oxygen here will be the excess. So that means if we use up all the aluminum, we still have some leftover of the oxygen. Then they just try to figure out what is the leftover. Then the good thing is, then we just need to figure out, okay, now I want to use up all the aluminum. I want to know if we use up all the aluminum, how many moles of the oxygen will be used, right? And then the leftover will be just the excess. So based on this 4.5 moles of aluminum, then it's a 4 moles of aluminum will react with 3 moles of the oxygen. So now in this case, we will figure out how many oxygen that can be used up if we use up all the, can be used if we use up all the aluminum. So 4.5 times 3 divided by 4. I got 3.375. 3.375 mole of the oxygen. So that means if we use up all of the aluminum, we're going to use a 3.375 moles of oxygen. So obviously, we totally has 3.5 moles of the oxygen. So obviously, we have still some left over for the oxygen, right? Then you subtract the 3.375, the difference will be just the leftover, right? The difference will be just the leftover, which is 0.125 mole of the oxygen. That makes sense, right? That makes sense? All right, so now you can go ahead and work on the similar question, question number 8. If you're finished the question number 8, go ahead and work on the question number 11. Okay, so let's looking at the question number 8. This is a similar questions for the, just like the question number 7. Okay, it's a similar. So let's work on this one. We have 4 gallium plus 3 moles of oxygen. Then they're going to generate 2 moles of the gallium oxide. Okay, so again, we try to figure out which one is the limiting reagent since we have a 0.48 moles of the gallium and 0.39 moles of the oxygen. And once again, you see, to figure out, to determine whether this question is a limiting reagent or just a normal stoichiometry, how do we determine that? You see whether this question give you 2 number or just 1 number. You see, this question give you 2 number and give you the number for both reactants. But if you're doing the normal stoichiometry, there's nothing. Okay, they only just give you 1 number of one of this reactant. All right, so now we try to figure out based on the, if we use up all the 0.4 moles of the gallium, how many moles of the product that we can generate it. So 4 moles of the gallium will generate 2 moles of the gallium oxide. And then you will see this is a 0.24 moles of the gallium oxide. And then if we use up all the oxygen, which is 0.39 moles of the oxygen, how many moles of the gallium oxide that can be produced? 3 moles of the oxygen will produce 2 moles of the gallium oxide. Okay, so now you can see 0.39 times 2 divided by 3, 0.26. So we have a 0.26 mole of the gallium oxide. Okay, now in this case, we just compare those two. Okay, then we're going to choose the smaller number. The smaller number, and again, this is not called the limiting reagent. That is just a theoretical yield, which is the maximum yield that can be produced by the limiting reagent. And the gallium up here is the what we call the limiting reagent. In another word, oxygen will be the excess. Oxygen will be excess. So here talk about how much is remain for the excess. Then we just need to know how much oxygen has been used up, right? Has been used. The difference will be the excess. Now we use up 0.48 moles of the gallium. And then how many oxygen will be used if we use all the 0.48 moles of gallium? Then that's 4 moles of the gallium will be react with 3 moles of the oxygen. So then you can figure out 0.48 times 3 divided by 4, 0.36. So now we have 0.36 mole of the oxygen is being used. So the difference, 0.39 moles of the oxygen, subtract 0.36 mole of the oxygen, the difference will be 0.03 moles of the oxygen. Makes sense, right? Yeah, makes sense. Okay, so this is just a mole to mole ratio, right? The question gave you the mole. But if the question gave you the mass, actually is doing the same thing. So that's why I gave you one of the question 11. It's just a little bit challenge, but generally the logic is the same thing. Okay, so now we have 2 moles N2O4 plus N2H4 and react with 6 moles of the nitrogen and plus 2 moles of water, right? And the question asking for, now we have what is the maximum mass of the oxygen that can produce? What does that mean? Maximum mass here. If we convert that to the maximum mass over here, that means it's just a theoretical yield Okay, so you talk about what is the theoretical yield that for the NO for the NO. Okay, so now what we have a 15.5 gram of N2O4, and we have a 4.68 gram of the N2H4. So now you just need to, based on the mass over here, try to figure out the mass of the NO, right? Well, it's nothing with the water, so you don't have to do anything with the water. You don't have, right? We just need to just assume if we use up all the 15.5 gram of this, how many moles of oxygen we produce? If we use up all the moles of the gram of the N2OH4, how many moles of the NO we produce? And we compare which one is smaller, and then we can determine which one is a limiting reagent. And then meanwhile, we will figure out what is the maximum, what is the theoretical yield. That makes sense, right? Yeah. So that's why let's just work on this. Okay, we're very similar like what we did over here. The only difference here, this is in mole and this is in gram. You just need to convert that from mole to gram. That's it, right? You're just doing the conversion. But again, you can using one step, one equation to figure out. So now we have first, let's do N2O4. We have a 15.5 gram of the N2O4, that's in mass. So what are you gonna do? You need to divide by the molar mass, right? Divided by molar mass, then you got from gram to mole. So last time we talked about N2O4, that's 92.0 gram per mole. So 92.0 gram of the N2O4, that's worth 1 mole of the N2O4. Then typically that is just the molar mass, right? Because 1 mole of the N2O4, that's weight is 92 gram. That is the meaning or definition of the molar mass. Okay, that definition of the molar mass. So gram of this is canceled. Now, based on this, generally you just figure out the moles of the N2O4. And then you're using the stoichiometry. 2 moles of the N2O4 will make 6 moles of the NO. So 2 moles of the N2O4 will generate 6 mole of the NO. Okay, still the similar things. You're still going to figure out the moles of the product, right? NO, and try to figure out which one is the limiting reagent and which one is the theoretical yield. Well, you don't have to get the gram. The first purpose is try to figure out what is the limiting reagent, right? We're just using mole, that's completely fine. Okay, so most of that canceled. You can figure out, okay, if I use up a 15.5 gram of this, well, how many moles of the NO we can generate it? 15.5 times 1 times 6 divided by parenthesis 92.0 times 2 parenthesis. So we got a 0.5054. 0.5054, and that is a mole of the NO. We got that much moles of NO. Okay, and then we're going to do the same thing. So what if we use up all of the N2H4? Okay, so we have a 6.468 gram of the N2H4. Again, you divide by the molar mass of the N2H4, which is 32.0 gram of the N2H4 equal to 1 mole of the N2H4. So after this, you got a mole of the N2H4. And based on the stoichiometry, 1 mole of the N2H4 will generate 6 moles of the NO. Well, then you just based on this stoichiometry to figure out how many moles of the NO that we're going to use, we can produce based on the N2H4. So 4.68 times 1 and times 6 divided by parenthesis 32 times 1. We got a 0.8775. 0.8775 mole of the NO. So now you see we got the 2 of the NO, then we just need to compare those two numbers. So obviously that one will be the smaller one. So this one is what we call the theoretical yield. In another word, this is going to be the maximum yield or maximum amount that produced by the limiting reagent. So this is the theoretical yield, and which one produced that? N2O4. So N2O4 will be the limiting reagent. Okay, N2O4 will be the limiting reagent. Well, then you see the question actually is asking for the maximum mass. What we have, we're having moles. So we try to figure out what is the maximum mass. Then what are you gonna do? You're just using mole, the theoretical yield, 0.5054 mole of the NO. Then you multiply the molar mass of the NO, then you got a mass, right? You got a mass of NO. The molar mass of the NO is just a 30.0 gram per mole, right? You see, this is a gram of the NO per 1 mole of NO. You see the moles of NO can be cancelled, then you will got the answer, which is 0.5054 times 30. You got a 15.162. 15.162, and this is in gram, which is the mass. Okay. Now, since if you're looking at the question, all the question give you 3 sig figs. So the answer will keep 3 sig figs. So that's 1, 2, 3, and keep the next one. Next one is 6. You round up to 15.2 gram. Makes sense, right? Okay, but the strategy, the thought, the pathway is doing the same thing. We determine, okay, if we use up the first reagent, what is the product can produce? If we use up the second reagent, what is the product that can produce? Okay, and then we'll compare those two products, choose the smaller one, and then we go back to figure out which one is the limiting reagent, and that's it. That makes sense, right? So is this way is more easier than the way that in the video, right? What do you think? Okay, yeah. So now we're done for today. Okay, yeah, I definitely will give you the practice for in the homework. Okay, yeah, and also remember we are going to have a quiz on next Monday. The quiz will be just talking about stoichiometry and limiting reagent. Okay, stoichiometry and limiting reagent. Okay, and I think that's it. Okay, yeah. So let's pack things and we will move to the lab.